Hi everyone. Today, the equilibrium law. This is a kind of a calculation where we're going to be solving for a number that represents the ratio of products to reactants. The values that we're going to be inputting into our calculation are molar concentration, so values in moles per liter. We're going to see square brackets a lot of the time, and that's a way to indicate concentration. The number that we're going to be solving for using the equilibrium law is called Kc, which is the equilibrium constant. This is an interesting value. It's a number that does not have units, but the significant digits, we're going to follow our traditional significant digit rules. Here's a generic equation. Chemical A reacting with B in equilibrium with C and D. What we see though is the capital letter represents the chemical itself, and the lowercase letter is the balancing coefficient. So we have chemical A balanced with lowercase a reacting with chemical B balanced with this lowercase b in equilibrium. Notice that double-headed arrow with chemical C and D. What we're going to do is calculate Kc by doing products over reactants. It's the concentration, there's those square brackets, the concentration of chemical C in moles per liter to the power of how it was balanced, multiplied by the concentration of chemical D in moles per liter to the power of however it was balanced, over chemical A to the power of how it was balanced, and then chemical B. One interesting thing about these equilibrium law expressions is that we're never going to include liquid water. Liquid water itself isn't going to have a concentration, so we're going to not include it in our equilibrium law expression or calculation. Interestingly, the equilibrium law is going to be different for every equation. There might only be one reactant, or there could be just one product. Okay, so here's two examples. I have nitrogen gas reacting with oxygen gas in equilibrium with 2 moles of nitrogen monoxide, 2NO. The Kc expression is going to be the products over the reactants. There's just the one product. So there it is, NO, and it's to the power of 2 because it was balanced with a 2. The concentration of nitrogen monoxide gas in moles per liter to the power of 2 because it was balanced with a 2 in the equation. Divided by, there's 2 reactants, so they both show up in the denominator position of the equilibrium law expression. The concentration of the nitrogen gas to the power of 1. Notice there's no exponent there because this was balanced with the 1. Multiplied by the concentration of the oxygen gas. A second example, quite an involved one actually, has these 4 moles of ammonia gas reacting with 5 moles of oxygen gas to produce 4 moles of nitrogen monoxide gas and 6 moles of water vapor. Equilibrium law expression, Kc, is going to again be products over reactants. So we have the 2 products in the numerator position, the concentration of the nitrogen monoxide to the power of 4. It's balanced with a 4 up here, so it's to the power of 4. Then we have the water vapor. We are going to include water vapor. It's only liquid water that's not going to be included in our equilibrium law expression. We have the H2O gas to the power of 6, because it was balanced with a 6 as its coefficient in the equilibrium reaction. This is over the ammonia, NH3, to the power of 4, and the oxygen gas to the power of 5. And I hope that helps.